Hey guys, so this is Physics 1111, first semester algebra based review sections for the final test. So for a final exam, it's not more than one exam, it's just one exam. So we'll just leave it at one exam. So we've got some coverage to do. We're going to do it now. Momentum. Let's carry on. We've got momentum is equal to mass times velocity. The velocity is a vector, which means and mass is a scalar, which means our momentum is a vector. So the units of that are kilograms, meters per second. And just a side note, this is a little p, okay? It's not a big P, it's just a little p, small case p. So what is the relationship to the second law? Well, what is the second law? F equals ma. Now this is the net force, so that's our net acceleration. And of course that equals the sum of all the forces that are being acted, that it's being acted upon, this mass. So we can go from 1 to n different forces. Our mass times our acceleration turns out to be equal to our delta P over delta T. So if we have a change, delta P is equal to our mass times our velocity final minus our velocity initial, then we're going to easily be able to see that let's just say P final minus P initial, and then we can do something like this, delta T, and that gives us mass times our final velocity minus our initial velocity. To prove it, do we need to prove it? I'm not going to prove it. You can read about it in the notes. Yeah, there's no sense trying to prove that. We're just going to go with it the way that it is. You'll see that the proof is there. Let's move on. This takes us to the equation that we call the impulse equation. And that impulse equation is delta P equals our F net, okay, not just one of these, it's got to be the net, okay, it's got to be all of them, so added together. So the F net times T, okay, so F net times T is our impulse. Okay, so that's big, and then you have to keep in mind that F net is equal to all of those guys added together. So that's the sum of all forces. What happens when delta P is equal to 0? Well, if that equals 0, then this, is the time going to be equal to 0? No. Time, nothing happens in no time. So things have to happen in time. So F net then must be 0. So When that happens, let's look and see what happens up here. Our acceleration is 0. Delta P equals 0. So this guy's not 0. The mass isn't 0. So that means V final equals V initial. So I don't know why that initial won't. Okay. That means we could have more than one mass. Okay, so if we do have more than one mass, we have to consider all the masses. And in general, we consider all, that's 2, 0, m3 times 3, 0, and that's got to equal all of the velocities 1 final plus m2 v2 final plus m3 v3 final. Okay, so these are all of our initial velocities, these are all of our final velocities, but keep in mind, it's momentum that is being conserved, so you have to multiply by the mass, otherwise you're in trouble. So don't try and get hasty and skip out on your masses because they may not all be the same mass. Okay, only if they are the same mass can you eliminate them from both sides of the equation, if it's possible. Okay, so what does that mean? These are the external forces acting. Okay, so those are external forces acting on our mass. Okay, so those external forces all have to end up being 0 for our conservation of momentum. Okay, so what do we have? We've got elastic collisions and inelastic collisions. So elastic. Let's look at elastic. Elastic can happen in 1 or 2 dimensions, and you guys should be ready for that. Elastic means what? What is the meaning of an elastic collision? It means delta KE equals 0. What does that mean? Our kinetic energy final minus our kinetic energy initial equals 0, or kinetic energy final equals our kinetic energy initial. So that's what that means. And you can't just cancel out masses willy-nilly and go straight to v squareds because the 1/2s cancel and all that. You have to do 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared equals 1/2. If this has got 2 masses in it, okay, if our problem has 2 masses, then you have to keep the masses aren't going to change. v1 initial squared plus 1/2 m2 v2 initial squared. All right, so yeah, so the masses aren't going to change, but they aren't the same either. M1 is different from M2, so you have to keep that in your equation. But what you can get rid of is these 1/2s. You can chop those out. But that's pretty much it. Since in general our work net is equal to delta KE, but in our situation, delta KE equals 0, we have 0 equals work net. Okay, so in an elastic collision, the collisions between the bodies simply transfer energy between them. Okay, so we have bodies that are going to come together. They're going to have this interaction, and then who knows, we'll call this one 1 and this one 2. And who knows what's going to happen, 2 and 1, and they'll do something, and fine, that's great for us, but what they're doing is transferring momentum in a way that conserves momentum. So the initial momentum and the final momentum are conserved, so they're equal to each other. But we also have to conserve energy as well. So the two things are conserved. And I want to do one last thing. Why would I say that's a y when it's really an x? If we have our definition of x and y like this momentum conservation is conserved in the x direction and the y direction. Do not try and do both at the same time. Okay, so px and py are conserved. Okay, if we're dealing with this type of two-dimensional situation. So you have to break it up into x components and y components. There's no way around it. Everyone has to do it. I do it. All the physicists all around the world do it. You have to do it as well. Okay, so what about an inelastic? So we've got our inelastic collision. Of course, this can also be done in 1 or 2 dimensions. They don't conserve, so kinetic energy is not conserved. So something has to take energy out of the system. So let's put KE final is not equal to KE initial. So we've got 2 ways of doing that. The first way is perfectly inelastic. So perfectly inelastic. What are we going to do? What do you think is perfectly inelastic? Well, that would be when the 2 objects glom onto each other. So one object and the other object come together, and finally, when they leave, we've got 2 objects glommed onto each other. Okay, so initially they're separate. In the end, they're together. That's perfectly inelastic. So what is another way we could do this? Well, we could have one of the bodies or both of the bodies get deformed, and we just call this inelastic, not perfectly inelastic. But our body comes in pretty non-deformed. These are perfect circles. You can't tell, but yeah, they are. That's perfection for you. And then when they leave, they're dented. So now all of a sudden we've got these things that are dented. They've been hit, okay, and it's obvious, right? Like cars in Rome. So that is that's what happens. And things happen. Well, the energy that was lost from this kinetic energy, the energy that was lost is lost due to deformation. So energy, I'm having a hard time spelling today. Energy is lost due to deformation of the items, of the objects that are going in, right? Object 1 and object 2, object 1 and object 2. All right? Okay, so we've got inelastic, we've got the perfectly inelastic, and we know that delta Ke, now, what could we do? The energy loss is equal to our delta Ke final minus our Ke initial, so that's delta Ke. Our energy loss could be found, and we'd know how much energy went into the deformation. So this is energy into the deformations. So they're not going to give it back, right? They've been deformed. You have a car accident and your car gets pushed in. It's not snapping back out. You got to go to Better Get Mako or whatever, and you go in there, and then they help you repair the work. They have to do work, right, to get that repaired. That work is energy put into your car to pull that dent out or repair or whatever it takes. So I'm going to iterate it again. You have to do both X and Y directions. Okay, so awesome. Yeah. All right. So to do X and Y, let's look at momentum in both the X and Y directions. So we've got X gives us our P naught X. And of course, that's our M1 V1 X plus all the others V2 X. Initially, we better have a initial on there, plus blah, blah, blah. In the Y direction, we have P naught Y, and that's equal to M1 V1 naught Y, M2 V2 naught Y. So you're carrying around all these little markers as you go. And all of that has to be equal to our P final x. So our P final x then is equal to our M1 V 1 final x. Gosh, takes a lot of brain power, right, to just write down these. And then P final in the y, M1 V1 final in the y, M2 V2 final in the y. So, okay, so let's draw a little diagram. This is our P final, our momentum for one of the items finally, okay? And we have to break that down into P1 final X. So let's say that this is our question. We want to know what that is. Well, we have to break it down into X and Y. Okay, and then of course there will be some angle there. And P1 final Y will equal a bunch of stuff, right? P1 final Y would equal all this stuff. But not necessarily all that stuff. You know what? Let's get rid of the ones. And we just want to know what the P final is. I'm making it probably more complicated than it is. We just want to know P final. Okay, so we have to figure out P final in the Y, which is a bunch of stuff. So that's just a number, but it's made up of all the stuff and all the momentums, number of all momentums in the Y direction. And then we have to have P final X, and that's also just some number that's made up of all momentums. Oh, I shouldn't have had pizza for lunch. It's making me sluggish in the X direction. So then we can do Pythagorean theorem, of course, to get our P final. P final Y squared plus P final X squared, and then we're going to take the square root of all that, and great. Now what about theta? Because if we want to know P final, we have to have a theta, right? We have to have the magnitude which is what we get from here. Okay, that gives us our magnitude and a direction at theta. And then we would say with respect to some axis. All right, well, in our case, we're with respect to the x-axis. So theta is with respect to the x-axis. In fact, it's not just the x-axis, it's the positive x-axis. So with respect to the positive x-axis, all right, so how do we get theta? You guys have done this, and hopefully a few times. We just take PFY and we divide it by PFX. If you put the x in the denominator, it'll be with respect to the x-axis. Now, if both of these are negative, then you're not looking in the positive x-axis, you're looking in the negative x-axis. Or maybe just the bottom one is negative. If that's the case, then you're with respect to the negative x-axis when you do this, okay? So, yeah, keep that in mind. All right. Good. So, excellent. Excellent work by us. Just, I'm not going to go over trigonometry anymore. It's in this. You can get it. Set timer for 30 minutes. We're going to go 30 minutes, and then whatever's remaining, I'll finish up, because I don't think we're going to finish all of this in 30 minutes. So, we've talked about equilibrium conditions. Okay, so let's get back to statics. And when anybody says statics, that means equilibrium. Or whenever anybody says equilibrium, they mean statics, right? So they're almost the same thing. So we've got statics, which is the whole classic static situation, and equilibrium decides if we're in equilibrium, then we are static. So let's look at statics and some torque. All right, we've talked about equilibrium conditions already. You guys hopefully have these drilled into your head. F net equals 0. Okay, and of course that implies that A equals 0 because M can't be 0. M cannot be 0, otherwise it's not an object. And that A equals 0 means that V is either equal to a constant or 0. 2. Torque net. So our torque net is equal to 0. That implies, because our I, normally it would be equal to I alpha, but I cannot be 0, so that means that alpha must be 0. And that implies omega is either equal to a constant or 0. Okay, so if somebody gives you a problem and they say omega is constant or V is constant, if it's a rotational problem, omega will be constant. If it's a static situation. Okay, so then you can apply this and this. So fabulous. Let's look at a bar of length L, and we've got position 1, we've got position 2, and those are places, L over 2, those are places where you could put pivot points, okay, and you could have it pivot about in this direction, or you could have it pivot out towards you or into the page, okay, so either into the page or out of the page at this point. It could be pivoting that way as well, okay, so there's the third one, right, where we put an axis right down the middle, and it could be rolling, in other words, So we could be coming into the page here and out of the page here around that axis. So yeah, so there's the three axes that you could rotate about. Typically we do this one or this one, and I don't know, quite often we do this one actually. So it'll be one of those three. So now we're back to rotational motion. What happens in rotational motion? Also, by the way, when this is rotating, if omega is a constant, we're talking about statics and equilibrium. So omega could be this rotation in omega. It could be this rotation in omega, right? This is this one. It could be this rotation in omega. Okay, so wrap your brains around those. But omega is the constant, okay? It could just be sitting still and not doing anything. So then in that situation, we would have 0, omega equals 0. So let's look at a little bit of our conversions. Oftentimes, x is represented as s. So you have this circle, it rotates some angle theta, and the distance here is x, right? But they call it s in the books so that you can keep track. But theta equals x over r, or s over r. It doesn't matter. If you're dealing with theta and r and a linear situation, it's s or x. It doesn't matter. So we can also, why would I say that? Oh, yeah. No, that's good. Fine, I like this. Omega is that, and then alpha is, and I really want a delta on those because in my book here, I don't have a delta on them, but should be, okay? So, should have a delta. All right, so let's continue on with our torque. We've got our torque. And of course, it equals the radius times the force times the sine of the angle between them. And that's in meter newtons, okay? That is not a joule. It's meter newtons. And just so that we can see these things happening, here's our radius. Let's say this is our force. All right, so we can pick up our force. We've added them head to tail, all right? But we can pick up that force and we can put it here. And now we've got some angle between them. Well, it turns out that that angle is the same as this angle, so you don't actually have to do what I'm doing. You can do it this way. At any rate, that's our angle between them. And essentially what we're doing when we do this is we're taking the component, the sine component of that force. So this is F sine theta. We're taking the perpendicular component to the radius. Okay, so that's what this does for us, is it takes the perpendicular component. Okay, and you can do the same thing You could assign it to the R if you want, and we can break the R up into its different components. You know, play around with it however you feel comfortable doing that. So if torque is equal to 0, that means something in here equals 0, but we know this can't be 0. The force that is applied is the net force, so that actually could be 0, or the sine of the angle theta could be 0. And if that happens, that means that R and F are completely in line with each other. And if they are, then the angle between them equals 0, and the sine of 0 is equal to 0. So there's that. Now, that's statics. Okay, now let's get into the dynamics aspect of it. Our torque net is going to equal our moment of inertia times alpha net. Okay, and that is going to be equal to R times the force net, where it's being acted upon, times the sine of the angle between them. I depends on the axis of rotation, right? So depending on which axis of rotation we've chosen, so we've got 1, 2, or 3, those 3 axes. It depends on that. So let's say I1. I1 equals ml squared over 3. I2 equals ml squared over 12. And in that situation, theta is equal to 0. So we can then get rid of the sine of theta, and we can just say that I alpha is equal to R force. And then, like I said, you could have many forces. So we could have R1, force 1, plus R2, force 2, plus blah, blah, blah. And I just saw a problem with my notes that I posted. So is it the cosine that we're dealing with there? No, it's not. So do not use cosine. If in general we're doing this, we need it to be the sine. The torque is the sine, not the cosine. So I have to fix that and rescan. I have to fix that and rescan. So plus R2 F2 sine of theta. Okay, so we've got 2 cases. We've got the case where we're going around, circling around number 1, that uses I1. So let's call it case 1. We've got case 2. Case 2. And let's get into those 2 different cases. I1 alpha is equal to the length L times the force of 1. If we apply a force of 1 at a length L. So what we're doing is force 1 there. And that equals our ml squared over 3 times alpha. And then that implies, right, we can solve for F1 as ML over 3 times alpha. Okay, case 2. So this is case 1. Case 2. I2 alpha equals, now in this situation, our force has now become force 2, but we're operating at this pivot point instead, 2. So F2 is still being applied, but now the distance is L over 2, okay? So we have to say L over 2 times F2, and we can insert what I2 is equal to. We get that over here. So F2, let's do it. I2 is ML squared over 12 times alpha, giving us F2 is equal to, it looks like we're going to have 1/6. So we'll have ML over 6 times alpha. So 1 is half of the other. The force required, okay, that what we just calculated is the force required to move that at the same alpha, okay, with the same torque. So that's what we just did. Should I write that out? So torque in case 1 is equal to torque in case 2. All right, and we figured out that due to all of those different things, F1 has to be equal to 2 times F2. That's what we did. And it makes sense, actually, if you think about it. If we go back to, sorry about that. If we go back up here, of course, the force, if we apply a force at that same spot, force 1 or force 2, of course we have to do twice the force if we're doing twice the lever, okay? So that makes sense. All right. So let's keep going. Right, and so I didn't say it out loud, but it's easier to spin the bar in case 2. So lower moment of inertia, easier to spin. So let's look at some statics again. So F net is equal to 0. Tau net is equal to 0. So we're definitely in a static situation. We've got 3 equations. We've got the x direction, where Fx net is equal to 0. We've got the y, Fy net is equal to 0. And then we've got our third equation that's just because torque is just torque one way or the other. So it doesn't really have an x or a y, so we just say torque net is equal to 0. Okay? And that gives us a whole bunch of equations to work with. Fx net is equal to the sum of all, what's that movie? Sum of all somethings. Anyway, Fx1 plus Fx2 plus ... Fy net is equal to Fy1 plus Fy2 plus dot dot dot. And torque net, of course, is there's a bunch of ways you could do torque net, but the best way would be R1 F1 sine of theta 1 plus R2 F2 sine theta 2 plus blah blah blah. Okay, that I don't like the way I've got it written there, but each of those have to be perpendicular. So the way I've written it on the thing, RF have to be perpendicular to each other. Otherwise, you need the sine of theta in there if they're not perpendicular. There are many ways to solve these three equations, and it all depends on what you want to know, what you're given, and what you don't know. So that's a tricky bit that is pretty much up to you. Nobody knows. I don't know. It goes on a case by case basis. Depends on the problem, right? So what are the keys to this? The main takeaways. First, select a pivot point. Okay, now, what we're saying here is, in the case of statics, you can select your pivot point. You can do it anywhere. You can do it anywhere you want. Okay, so it doesn't matter. So that's the first thing that you want to do is select a pivot point, PP, and you're going to do it so that it eliminates one of your unknowns from the equation. And then you can solve and hopefully come back to another pivot point that allows you to solve the next bit. So then second, move to another pivot point to solve another thing that you didn't know. And then you could keep doing that. You could just keep doing it over and over and over, but repeat as needed, right? Wash, rinse, and repeat. And then the third thing, make sure that you stick to your coordinate system. So in order to stick to your coordinate system, what has to happen? You have to define a coordinate system. Okay, so it's up to you to define your torque coordinate system. So if that's our pivot point, why did I write a B? Nobody knows. If that's our pivot point, then we are defining anything that twists in this direction, or a force that is applied that pulls it in that direction, is positive. That's positive torque. If it goes in this direction or this direction, it's negative torque. Okay? So positive and negative have to be accounted for. In order to do that, your job. This is your job. So if you haven't defined your coordinate system on a problem, you are hopefully dealing with nothing but, I don't know. I would define a coordinate system. I would definitely do that. Don't miss out on points. Stability. So we've got some stability things. We've got stable, our little ball in a bowl. We've got unstable, where we've got a ball. I'm going to draw unstable a little bit better. We've got a ball on top of a bowl, or a rock on something, it looks like. That is going to stay there, and if it's bumped, it's going to slide just a little bit. So it's got, it's perfectly symmetrical, and it's got symmetry working for it, but any slight little perturbation, and that thing's going to go whoosh. Here, where are we at here? Let me do this. And it's gone, right? So that is unstable. Let's write down V equals 0, A equals 0. This is definitely A not equal to 0 after perturbation, V increasing. Okay, whether it's going to the right or the left, it doesn't matter. It'll be increasing. Now, it does matter the sign, right? But either way, the absolute value of these things is greater than 0, not equal to 0. You know what? Not equal to 0 implies it could be negative. So I'm just going to leave that like that. Okay, super good. What's our last one? You guys, you know. We have neutral. And in that situation, we can bump this thing. We can bump it that way. We could bump it that way. If there's no friction in this situation, then V will be a constant. We've bumped it. It'll stay at that velocity until forever. Okay? If there is friction, V will decline until it equals V equals 0. Okay? And it's sitting still. All right? So this is with friction. And this is sans friction. Sans means without, or there is none. Okay. Mechanical advantage. Our mechanical advantage. You guys were good about that. On the last test, everybody knew Fn is in the denominator, F out is in the numerator, and that gives us our mechanical advantage. Excellent. Everybody, I was so pleased to see that. So let's do a thing where we have some pivot point or fulcrum. We've got L over 4 here. We've got a mass. Okay, I don't know. It's a thing. It's not a lump. It's not a tumor. It's a mass that is going down. Whoa. So mg I have no idea how that happened, but pardon me. Going this way, we are applying some force in, and we'd like to know what that force in is, right? Maybe. I don't know. The whole thing is L from here to there. So we've got 3/4 L to the fulcrum, L over 4 from the fulcrum to the mass pulling down, and we're going to do our lever. We're gonna say the sum of the torques, so torque net is equal to 0. Okay, we're keeping it still. All right, we're just having enough force to keep everything still. So torque net is equal to 0. That means that our F in times 3/4 of L is equal to our mg times L over 4. And there's a lot of different ways we can do this, but what's the way you want to do it? This is our F out. Freak out. This is our F in. Okay? So why don't we solve F out over F in? Okay, well, let's do it. F out is mg. F in, we don't know. But we also know that that equals whatever is left, right? So we've got mg on top. We've put Fn on the bottom. That leaves us with 3/4 L on top and 1/4 L on the bottom. Well, what's nice about that is these L's cancel. The 1/4 cancel, and we're left with 3. So awesome. This is our mechanical advantage. Now we know our mechanical advantage, and we could just say that our mechanical advantage means that our F in equals our F out divided by our mechanical advantage. So we could say that our F in is 1/3 our F out, which is mg. So we don't have to lift all of the weight. We only have to lift 1/3 of the weight. So our mechanical advantage in this situation, using a lever like this, has really helped us not have to push so hard to lift that weight up in the air. So, and keep in mind, it's static. We're doing it in a static situation. All right, let's do a little rotational dynamics. You know what? We're not going to do a little rotational dynamics. We're going to hold rotational dynamics for the next vid. We'll start off with rotational dynamics, and we're going to do that now.